All right, so this is requiring a few things. So it's got to be, so 24a says f prime of x is less than 0,
F double prime is also less than 0.
and f double prime of x is less than 0 for all x. Can somebody translate this into more, something closer to English? All right, what's this say in English? Don't say what I just said. Yeah. Yeah, so this function is always decreasing. There you go, that's all the way to English. I love it. Function's always decreasing. And then that says the function is always concave down. So it's got to always be decreasing, and it can't have anywhere where it has this wiggle in it like that, right? That's an inflection point. Has anybody tried that problem yet? Not enough people. This is one of those that if I show you, it's done. I can't get you started. Yes.
Section.
4.3. So I mean, it's got to be concave down, but why is this already wrong?
This is self-positive.
Yeah. See, that's concave down, but increasing, isn't it?
Yeah.
Okay, think about that. Can you do something similar, but just make it decreasing instead of increasing, but concave down? Maybe like the other side of the thing. I don't know. Think about it. That's as much I'm going to say.
So essentially, this is asking for a formula, us to provide a formula that fits both of those.
Not formula, just a graph.
Just a graph.
Yeah.
Does it need to be like a detailed graph? Or just like
Doesn't need to be detailed at all.
okay.
Yeah. No. You got it. No. I mean, if you want to make it detailed, as long as it's correct in terms of what this wants. This doesn't say anything about values of anything. No, it can be anywhere. Scale can be anything. You don't even need a scale really for this problem. This is a completely conceptual problem. This is one place where a graph, I'm not saying this is the answer, a graph like that would be great. You know, if it does everything that says it's supposed to do, then that's fantastic. I don't need scale for anything, right? This is one of the situations where that's fine. And then part B is just. Did I answer part B?
Yeah, it's the same thing.
Oh, that one's always increasing and always concave up. So you know, so why is that wrong for that part B? It's concave up, but it's decreasing. And again, there's kind of the other side of it. That's awesome. All right, that's one I can't really say much without just giving the answer away. Yes.
It's kind of an older problem, but so the radius of a saw blade is 26 centimeters. The error is 0.2, and then it asks us for the maximum amount of area given those two.
This is 310.
300.
What did it say again? The radius of a.
Saw is 26 centimeters. The error is 0.2. Find the maximum amount of area given that error margin.
Oh, okay. So I have a problem here. It says the radius of a circular disc is 24 centimeters with a maximum error of 0.2 centimeters. So the radius of a disc is 24 centimeters. Max error in the radius. What was it? 0.2? 0.2 centimeters. Use differentials to estimate the maximum error in the area of the disk. So, start with the formula for the area.
R squared.
And now do differentials. Yeah, but here, this is is this tiny? No, that's huge compared to how tiny it could be. So you don't want to do the D stuff, you want to do the delta stuff.
Okay, I think that's what I was saying.
mean, you could do the D stuff. It just is an estimate. Then that'll work too. You can do either one. And I think where to go? Yeah, on page 256 they talk about relative error. Relative error takes the difference in the thing divided by the thing. So if it was the volume, how off the volume could be divided by the volume. So they give you an example up there on the top page 256. And I think they give you, yeah, so you can use differentials. Bottom page 255, they give you an example that's a lot like that. Number 34, the radius one. Yeah. Yeah.
On 4.1, number 77.
Oh yeah, like so how would you, so it says prove that this function has neither a local max nor a local min. And the function they give you is funky. X to the 101, already awesome, plus x to the 51, plus x plus 1. In order to have a local max or a min, where does that happen? Yeah, and B. All right, so that works too. But, it's got to be where the derivative is negative and goes positive, or is positive and goes negative, right? So take the derivative. What do you get when you take the derivative?
101 x to the 100 plus 1.
Even power. Plus 1. Can this thing ever equal 0? This is plus 1, right? Can this thing be negative? It's always positive. So it's always increasing. How could it have a max or a min? See, there's nowhere that this equals 0. Yeah. This is positive, right? Do you guys see that?
Yeah.
Plus 1. So there's no critical numbers. Maxes and mins can only occur at critical numbers. Yeah. So, not every critical number shows up as a max or a min, but every single max and min has to occur at a critical number. Some of the critical numbers are just extra. There's where it's resting. All right. Anything else from homework stuff before we get back into where we left off?
On section 4.7, number 40.
Oh, yeah. I think you got a lot. So a boat leaves the dock at 2 p.m., travels due south at a speed of 20 kilometers an hour. Uh, 2 p.m. Where's he going to do? Another boat has been heading due east at 15 kilometers an hour and reaches the same dock at 3 p.m. So he's traveling due east. Let's see. Gets here at 3 p.m.
What number is it?
This is section 4.7. So this guy's going, what was it, 30 kilometers an hour?
20.
15. This other dude's going 15. Okay. At what time were the two boats closest together? Ooh, I like it. So if you at a time when he's here, when this guy reaches the dock, this is the dock here, right? When he gets to the dock, how far away is this guy?
20 kilometers.
He gets there at 3 p.m. Yeah, exactly. So it's been traveling for an hour, so he's 20 kilometers away. So at 3 p.m., this is the situation. Now, is my doing this going to directly answer the question? No, but shit, I'm going to do this. I'm going to kind of time slice it, right? I'm going to take a little snapshot at a time, just to kind of get myself from what the hell's going on here. Where am I? Oh, yeah. So he's 20 kilometers away. So obviously, any time after 3 p.m., they're only going to be further apart because this guy gets to the dock and he just stays there as far as I know, right? You guys with me? They don't say anything else about what happens. So you see, it's really interesting. You can kind of work this letting time run backwards. This is like the beginning, and then what's happening? This boat's getting closer to the dock. You guys with me if you turn the clock backwards? Because how far away was this guy? When he left, you can work that backwards too if you want to, just to have a beginning place. Do you guys understand what's happening? So, how far away is he from the dock? What do you want to call that? This one boat. How far away from the dock is he? What do you want to call this? X. That's crazy. I like it. That's what I'd call it, because it's parallel to the x-axis in my drawing. So he's traveling due east, heading towards the dock. How far is this guy away from the dock? Wide. And so at some time, how far apart are they? Well, let's say it's there. How far apart are they at any time? You do it. If this is X and this is Y, what's this?
Square root of the square plus 1.
Thank you. See what I did? I drew the picture. I'm trying to identify variables. Distance from the dock is a good variable to use because what's that 15 kilometers per hour then referencing? Change in what? X, there. So I can give it, and is X increasing or decreasing?
It's
Decreasing.
So it's negative.
So dx dt, negative 15. And what's dy dt?
20.
20. So this is your distance apart function. Right? And it's asking you, at what time were they closest together? So what are you trying to do with this?
As small as possible.
Smallest as possible. Trying to find the minimum. Right? So take derivative. So remember what we did about distance formulas? If you minimize d squared, you minimize d. So you can minimize d squared. So you don't have this ugly square root thing over everything. That would just make the whole thing much worse. Right? If you had this whole thing to 1/2 power, it would just, oh my god. No. So it's nice if I make d squared as small as possible. Obviously, I made d as small as possible. Does that help? Who asked that question? Right. Did it help you?
I think so. I'll let you know.
This is the best thing. Yes.
What unit homework was that from?
Section 10, 477. Number 48, right?
Yeah.
That's what you asked me. Okay.
On the website, it's only up to 4.5.
Up till where?
4.5.
Okay. Again, I think I said this on the first day. Just reminding you guys, if you are using WebAssign, you have got to let me know. It's not my first priority, to be honest. I don't really trust in online homework, but I make it available in case somebody likes it. You've got to let me know if it's behind. Period. Right? I'm pretty sure I said that on the first day. Okay. So yeah, I can put some more up there. That probably will help you for the test tomorrow. Yeah. All right. Anything else from homework stuff? I mean, really, I mean, this shouldn't be. You can take this derivative, right? And don't let this bother you. You're not doing implicit, by the way. Right? Call this the squared distance function. Right? So then it's just ds dt equals, and then you've got to do stuff over there. You guys see that? Okay. Anything else from homework stuff? We got one last section to finish up, and then we can do the review. Oh, poor little dude. Okay. Let's see. Does it? Okay. So we're about to get into a little bit of a window into how the calculator does something very specific. And obviously this is something from way before calculators, by the way. This is Newton's method. Newton was way back in the day. So here's the idea. Trying to find the roots of a function. One root at a time. So if I have some function, let's see, it goes. So there's two roots to this function, right? Let's say I want to figure out what this root is. And I take a guess. I can kind of tell it's close to this. There's my first guess. Call it x1. So here's the actual value at x1. Now, what Newton figured out is I can use the slope. If I'm close to the actual answer, then the slope should be kind of like pointing me in the direction of where the answer is, if I'm really close. In this case, the slope there would be kind of leading me to here, and see how much that would be my second guess right there. That would be x2. Let me stop there for a second. You guys see the idea? So let me do it with this other one. So if I wanted this one, let's say my x1 is like, oh, let's try to do it a little bit differently. Yeah. Let's say here's my x1. Here's the actual value. This is f of x1. Here's the tangent line there. And there's my x2 now. Would be the intercept with that tangent line. It would be the x-intercept of the tangent line. It's a better guess than first. Is it closer to the actual answer than my first guess was? Yes. And then guess what? I do it again. Right? I get this guy's value. I make a tangent line through it, and I'm just going to keep on getting closer and closer to that dang thing. There are certain functions, certain ways of behaving where Newton's method will just die. Or little Newton's method. Especially, you can imagine, one place it would die would be if it touches, if it's like that. I'm trying to find this. If I guess this, let me see if I can't make a nice one that would freak out. Oh, there we go. If I had one like that, and I guess something too far, if I guess like I'm trying to find this one, and I guess too far away, then obviously my tangent line's going to go crazy. Take me way the hell over there. So there is a little bit of, you got to be careful about the kind of function you're working with before you attack it with Newton's method. Your first guess being far off can throw any function off, but there are certain kind of functions, certain kind of behaviors that will throw the whole thing off a bit. Let's try to figure out how to put this into some math algorithm. So here's my first guess. Here's the value. How do I develop the tangent line, this tangent line? To f of x at x1. So we're going to develop the algorithm. This means it's not going to have any freaking numbers in it. This is just a general idea. And then we're going to be able to plug numbers into what we come up with. So how do I get the tangent line to f of x at x1? What do I need? Yeah, the slope and a point. So the point is going to be x1 comma f of x1. I love it. Very unsatisfying, but too damn bad. We don't know shit about the function, so of course we're not going to know shit about the specifics. But this is just the notation for what it would be. What about the slope? How do I get the slope at x1? What do I have to do? The slope at x1? What's the calculus word for slope? Derivative. So I take the derivative of f and evaluate it at x1. So real quick, a side note. Can somebody explain to me in words what that means? What that represents? The slope of the g function at x equals 2. I love it. Cool. So this is the slope of the f function at x1, which is exactly what I need for the tangent line at x1. It's got to have the same slope. So what's the tangent line equation now? What's the tangent line equation? That was fun. Sorry. You made that sound like what happened to you?
Y2 minus that one?
Y minus y1, blah, blah, blah. So y, let's do the whole thing. Y minus, what's the y piece of the point? F of x1. Y minus f of x1 equals m, f prime at x1, times x minus the x piece of the point. So my tangent line is f of x1. This should look very familiar. Instead of a, I've got an x1. Right? Instead of a, I've got an x1. Why do I have an x1 for this method? Why, Jeff? Why has it got to be something different than freaking a? What's your problem? Because that's my first guess, and then I'm going to have a second guess, so on x2, and blah, blah, blah. Makes more sense in this case. All right. Everything we've done is old news. Now I want to find the x-intercept of that tangent line. How do I find the x-intercept?
Zero for y.
Plug a 0 in for y. I like it. And solve for x. So 0 equals f of x1 plus f prime of x1. And I'm going to call my x-intercept, I'm going to call it x2, which shouldn't be amazing. That's my second guess, right? Is it pretty cool with that? I'm going to find the intercept. How do I do the x-intercept? I make y0, always. If you want the x-intercept, you make y0. If you have an equation with 26 letters in it, and you want the w-intercept, make all the other letters 0. That's crazy. I mean, yes, yeah. So if I solve for x2, if I solve for the x-intercept, I'm going to call it x2. Why? Because that's going to be my second guess. Solve for that. I have to subtract this divide by this, and add x1. You guys see that? I mean, just solve that for x2. Maybe I should just let you do it. Solve that for x2. If you're paying attention, I just told you how to do it. I always wonder if somebody comes into calculus thinking to themselves, oh, thank God, I'm away from algebra now. What? No. Algebra is learning to walk, especially learning to crawl. So it'll be negative f of x1 divided by f prime at x1, and then add x1. So let me put that up here. Boom. So I kind of look at this as my adjustment. There's my initial guess, and if I subtract this adjustment piece, it becomes better most of the time, unless my function's weird or my guess is really far away. How far is really far away? I don't know. If my function is doing this, and I want that intercept, I don't have to go very far away to be too far away. Right? If I go here, that tangent line, oh shit. If I go here, the tangent line, oh shit. If I go here, the tangent line takes me to infinity. That's off a bit. That's what I'm saying earlier about normally it's how close your guess is, but some functions require that definition of close to be stupid close, right? So, okay. All right, so if you have this, we just basically recaptured the formula for the next thing. Have you guys seen that notation? Because if I just do this whole thing again for x3 is going to be x2 minus f of x2 divided by f of prime of x2. So xn is xn minus 1. Which way did I do that? Yeah, good. xn plus 1 is xn minus f of xn divided by f prime of xn. That just captures any step I want to talk about. All right. So, let's do this. I'm not going to do those functions on there. Let's get a real actual function and try this out. Here. Okay. Oh, yeah. Okay, we'll do this. Why is there a root between -2 and 0? Somebody remember, if there's a root somewhere, what more than likely has happened? Sign changes, right? Does it have to? Be one of those where it just touches, right? But if the sign does change, then there must be a root. So at 0, it's 2. It's positive. At -2, what's true? The -16 minus 12 plus 2. That's big time freaking negative. So what's a good first guess for the root then? Okay, -1. So let's try first guess of -1, because that's in -2 to 0, right? Okay, so now here's how this built, and then I'm going to show you something in the calculator to make some of the little busy work shit quicker. Get this guy waking up. Shit. Yay. Okay. For this first one, we're not going to do any shortcuts. So to use this, how do I get x2? I take x1 minus f of x1 divided by f prime at x1. And my f function is this guy here. So what do I need to be able to figure this out by hand? The derivative. So what's f prime? Six x squared minus 6x. I like it. That's easy enough. So I get -1 minus, what's f at -1? Be -2 minus 3 plus 2. So it'll be -3. How's everybody doing so far? I mean, how did we develop that algorithm there? We just got the tangent line to the most general situation and then figured out the intercept. That's where that came from, right? Now that we've developed that, it's just a bunch of plug and shove. Too nice to believe, to be honest. F of -1 is -3. Is that cool? You do -2 plus 2 is 0, minus 3, so -3. What's f prime of -1? 12. Right? It'll be 6 plus 6. Thankfully, it's not 0. That's another place where it freaks out. If the derivative is 0, it freaks out. So what do you get here? Yeah, -1 plus 1/4. -3/4. So that's my second guess. That's x2. Why does it make sense that it got, if you think about it, remember 0 was 2, -2 was -18 or something crazy. Doesn't that seem like the root's probably closer to 0 then? And see how we got a little closer to 0? Now what do? Everything you just did again. So now x3 is going to equal -3/4 minus f at -3/4 divided by f prime at -3/4. So f at -3/4 is going to be particularly gross. Let's see. F at -3/4 will be -3/4 cubed is going to be -27/64 times 2 is -27/32. You guys like that one? We're just cubing shit and then double. Right? Cube this sucker, you get 27/64 negative times 2, so you just cut the bottom in half. Minus 3 times this thing squared, so you get minus 9 times 3, so that's going to be 27 over 4 squared, 16, plus 2.
Yeah, no, that's the very answer.
Okay, so you get -27 minus 54, because you need to have over 32 plus 2. You get negative 81 over 32 plus 64 over 32. Because it's over there like, you made it, Jeff, yeah. That's just that piece, right? So you get minus -17 over 32 over, now what's f prime at negative 3/4? Six times 3/4 squared, so that'll be 9/16 minus 6 times negative 3/4.
63 eighths.
Who's it?
63 eighths.
All right, I'll look that up. 6/3. So I get negative 3/4 plus 17 over 32 times 8 over 63. Right? Divide by a fraction, multiply by reciprocal. That goes in evenly, thank God. Oh, good job, Upti. Negative 3/4 plus, let's see, 17 has nothing in common with 63, right? Poor little thing. So you get 17 over 252, I think. Jump a line. 63, 189. You have negative 172 over 252, is that right? Something like that. I don't know. And that reduces all kinds of shit. Yes?
How do you know where to start, like the guessing?
Oh, yeah. Okay,
Do
so
you just pick a point in between negative 2 and 0?
you would never guess a number just without any foundation in anything. So either the problem is going to give you, like this one actually told you just to use negative 1. I at least wanted to show you a little bit more than that. That there, why is there a root in here? So what's a good guess? Something in the middle of those two, right?
Yeah.
All right. We're going to look in a minute at like an equation, how to use Newton's method to solve equations, not just find x-intercepts, but to solve equations. And then you've got to know what looks like it's close to the answer, so you have a different way to kind of figure out.
So like intuitively, we'll just be able to pick a point or
we'll
a
see.
number.
We just started talking about it. So we're going to go over a couple situations so you can see what you might have to think about, how you might have to think about it. Obviously, you always got your stupid calculator that can just tell you what the actual answer is, which is, I love it when I have a student like, can't our calculators already do this? I'm like, who gives the first shit? Who programmed your calculator? A human. How did they know what the hell to do? Because they knew this shit, right? That's more important. We don't want to be all like, was it the white-haired people in the time machine? There you go, something like this. Can't remember the name right now. All right. So this is getting kind of gross really quickly, right? Do you guys agree? So I'm going to have a way to automate this. It's kind of funny. This is doable by hand. Just a little gross. Yes?
I have another question. How do you know when to stop? Like, is it going to tell you to do it at a certain
It's going to tell you to get within a certain number of decimal places. So I'm going to show you a beautiful way to do this. The really funny thing to me is we're going to use the calculator to make it quick. And you're like, well, the calculator make it really quick, Jeff. All right. So let me show you that process in the calculator. And this is going to show you something that's actually got applications beyond just this one problem. There's ways you can use this calculator that I don't think you guys know about. Or whatever calculator you happen to use. I'm going to use a TI, because that's the one that's built into the system here. All right. So what I want to capture then is this, the xn, what was xn plus 1 equals xn minus f of xn divided by f prime of xn. This is kind of nifty. So the way we do this is, where do we start at? Negative 1. So let me say negative 1, store that in x. I don't know if have you used that store button in here yet? Have you guys? Store button's awesome. It's how you store something into a memory location. X is the easiest accessible memory location because there's a button devoted to X. You can use any of these other letters, A, B, C, D, see all those things up there? See all those letters? Those are all memory locations. Okay, I like it. What's cool about this is I can then just type in the actual parts of this using X. So xn is X minus, what's f of xn? 2x cubed minus 3x squared plus 2 all over 6x squared minus 6x. I'm just going to type all this shit in using x. Because what's the calculator know x is? Negative 1. Oh, let's see. There's even a better way to do this, but hold on. So let's see. Where am I at? Yeah, I'm thinking, yeah, maybe I'll do it that way. Yes?
Quick question. So, like, let's say we make x a number, and then we finish doing that problem. Does the calculator erase what we stored?
No, x will always be that until you override it. But I'm
So
thinking, go ahead.
Until, like,
It doesn't affect
When you do y equals, it uses a different idea for x. It's not. It doesn't give a value. Look, if I graph
thought it
this,
just, like,
it's the whole
permanently
graph.
changed
Yeah,
Okay.
it's not screwing with that. When you get your calculator, x has a value of 0 built into it. Not when you graph, though, because when you graph, it goes, oh, those are the special x and y's. So it differentiates that.
Okay.
Don't worry. But I'm also thinking I'm going to do this a slightly different way. I'm going to do this. This is actually the way I'm doing it now, which is fun. Instead of, I'm going to use, anybody remember what the ANS, what that has is the last thing on the screen? So if I use that, let me just do it and see if you guys get the idea. I think that's what I put on the paper, right? Did I put that on? Yeah, I did. Yay. So now if I say, now here's, to get this started, you hit -1, enter. So now that's in answer. So now I'll build that up. Answer minus, parentheses, 2 answer cubed minus 3 answer squared plus 2 divided by Jeff, man, show. It's been a rough day. 6 answer squared minus 6 answer. Now watch what's really cool about this. Doing it this way. Double check here. Let's do it once. The first time I hit this button, what better come out of this is -0.75. Right? That matches with a -3/4. And then whatever the hell -172 divided by 252 is, I don't know what that is. I don't even know. It's more than 0.5. All right, sure. -0.68? Is that like 2/3 almost? Anyway. Do you see, if I just hit enter again, it's going to, if I just keep hitting enter, it's going to recalculate what I typed in. But what is ANS now that I hit enter? How did I get this? Because now ANS is this. That's my next guess, and I want to plug that into the algorithm and go to town. And then I want to plug that back in, and then I want to plug that back in, and then I want to plug that back in. Now, can you tell me, can you see anywhere where I've gotten it correct to the 4th decimal place? This is 0.6777, if I'm round. This is 0.67765, 0.67765. Okay, so I know I'm probably good up to here. So if you just do this, if you have a list of it, you can actually see where it stops changing in what decimal place. And that's the decimal place that you're accurate up to at that point. If I just keep hitting enter, it's eventually not going to change at all because this doesn't show all of the decimal points. In fact, it's probably right now, yeah. That's as good as the calculator can get. Right there. No, yes, maybe, no. So real quick. Obviously, if you just put it in, 2x to 3x squared plus 2. There's one right there. See it? Yay! And you do the whole 0 thing. What's the left bound? Enter. What's the right bound? Enter. Where's my guess? 6776507. 677, 6507, you guys see that? 677, 6507? Yeah? Cool. So the calculator uses a modified Newton's method. I tried to contact TI to find out how they modified it exactly because I wanted to show you, and they said, we can't let you know that. Our competitors might get a hold of that shit. And I'm like, oh yeah. It felt sort of like a Willy Wonka thing where he's trying to get the gobstopper to give it to him. Give me that. Yeah. And Willie gets up at the end. Oh, you did it. Here's a calculator for you. Thanks. Too far with that Willy Wonka thing. So, let me see. Did I give you one on here to try? No. So let's look at an equation. Let's see how to use this thing for an equation. So, something like natural log of x equals sin x plus screw it. I'll just explain the second one. Now, if you know what these things look like, so let me see. Pi over 2 is like 1.57. So here's sine, right? Here's sine's doing its thing. And now natural log, where does it cross through the x-axis, natural log? Natural log of what is 0? 1. Natural log of 1. So it's going to be, so right here, this is 0.7, 1 is right in the middle there. So if I just kind of do this rough sketch, I get a not bad idea for initial guess. If I say pi is like 3, and again, this is all just an estimate. If I say pi is like 3, this is like in between these two. What would that be in between these two? 3 pi over 4. So 3 times 3 over 4 is, I can just, let's just make it 2. You guys understand? I mean, so if I say pi is 3, this would be 9/4. I don't want, so if I make this 8/4, that'll be 2. So that's my first guess is 2. So again, if I draw a rough sketch, I know this is a very rough sketch, but it captures the basic idea of ln and sine. Are you with me? And can you see how they're only going to have, probably only going to have one place where they meet, because this is going to keep rising up and up and up. In fact, where is the output 1 for ln? ln of what is 1? E, right? ln of E is 1, and then it goes up from there. So at the time it's at pi, it's above sine forever. How much of what I just said do you really have to get? None. Not really. But the question was, how to get a good guess for an estimate? Well, when you're involving functions, you should know the look of them. You can give a rough sketch of them. It gives you a rough estimate of where the intersection is.
And then you just pick a number.
Now, yeah, well, again, I didn't do all this work and then I went 7. No. So it looks like they meet at roughly 9/4. So I just made it 2 just to make it a nice first guess. Right? Or you could use 9/4 exactly if you wanted to.
So it could be like graph the function that we're given and then like eyeball it and then pick a number.
Yeah, in fact, sometimes I'll ask that question specifically. Graph this by hand, give a rough sketch by hand, which is why I love it when it's like perfect. You know? Like, no, look at that, that's crap, but it's good enough. All right. Now, how do I construct what f is, though? That's the real heart of this. That's what gets everything going, is what's f. So Newton's method is always about finding the x-intercept of two things, of a function, not two things, but of a function. What is the function I'm talking about then? What is it that I want to make equal to 0? ln of x minus sine x. That's what I want to be 0, right? So when you're trying to solve an equation, you leave it alone. Maybe you can sketch a graph, get a rough estimate of what the answer is to the equation. But then what's the f you're dealing with? Get one side equal to 0. Newton's method is all about finding the zeros of a function. That's what it does. So what, yes?
Doesn't matter.
It doesn't matter. You could have made it sine x minus ln x. Doesn't matter. So what's my f? What's my f of x? What function do I want to make equal to 0? ln x minus sine x. Cool. And now I can just start putting together my algorithm, right? So what do I need? I need f prime. What's f prime going to be? Cool. So now I want it to be, just like we did before, I want it to be answer minus f of answer. So what would f of answer look like? It would look like natural log answer minus sine answer divided by f prime at answer. So it'll be 1 over answer minus cosine answer. And again, this a and s is just like a little variable in itself. I just what I'm replacing x with to make it more directly related to the calculator. So if you have a calculator, go ahead and try this out. See how it works. What did we say our first guess was? 2. So put a 2 in there and hit enter. So then it's in a and s. It's in temporary memory. The mistake people make is not being careful with their parentheses.